Welcome to online training session day 8 part 2. In this I am going to cover the size optimization. So this is the training series details where we have covered the 1D meshing. Day 1 as FEM theory, day 2 as 1D meshing, day 3 as 2D. In day 4 I have covered 3D meshing. In day 5 I have covered analysis and post processing. Day 6 topology optimization. Day 7 I have clubbed with topography optimization and composite optimization. Today I am going to cover day 8 size optimization, last part, that is part 2. Earlier I have covered the part 1, and also I have divided the day 9 into two parts, part 1 and part 2, where I have to discuss about shape optimizations. So the topic which I am going to cover in today's training session is optimization of horizontal tail plane, then pre-sizing nonlinear gap optimization on airplane wing rib, minimization of maximum stresses of a rotating bar, size optimization, then manufacturing constraint in pre-size optimization of a composite structure, and size optimization using external response, that is D response property 3 through HyperMath. So let's start with the first problem or the first tutorial for this today's training session, where I am going to discuss about optimization of horizontal tail plane. So the purpose of this tutorial is to optimize the thickness of aluminum ribs for a horizontal tail plane as shown in the below. It is assumed that the tail is cantilevered about its inboard section. Three loading scenarios are considered: one where the tail experiences pressure load of 0.25 psi on the bottom skin, second where the tail experiences a tip load of 400 lbs, and a third where the tail experiences both the pressure load and the tip load simultaneously. The applying loading condition is represented in the following figure. As you can see, the material available for this part are described in the following table. Here is the table where we are going to use these materials. We can create this material with the two ways. First is simple way of clicking on material collector icon and create a material, or as we are going to have this composite laminate, so we can use a tool of HyperWorks, that is HyperLaminate, to create these materials. So we'll use the second one, which is HyperLaminate. Then in this tutorial we will see how to create material and geometric properties with HyperLaminate, create static and buckling subcases, perform baseline finite element analysis, run a size optimization, and compare the results with initial design. The optimization problem here may be stated as, for this problem is, my objective is to minimize the mass, my constraints are composite skin must not fail, aluminum ribs must not yield, buckling must not occur, and my design variables are composite ply thicknesses and the rib thickness. So we'll see. So we'll open the HyperWorks version 12. So if you are using HyperWorks Student Edition, you will not get these options, but you will get definitely the OptiStruct radius. So select the user profile as OptiStruct. Selecting a user profile means it will load the appropriate templates, macro menus, and import readers, paring down the functionalities of HyperMesh to what is relevant for generating the model for the OptiStruct solver. So we'll select the user profile as OptiStruct so that we can perform the buckling. We can perform the static analysis or as well as optimization using OptiStruct. So we'll open the model. So to open the model, click on Open Folder at the right top of your screen. Select the location where the model is. So this is my model, where the materials, some of the material properties, components, load collectors are predefined. So you can see that these are the predefined data available with us with this model. So we will proceed further with the where we will update some of the data and input some of the data to perform the required analysis. So first step is to create the isotropic material and property and assign it to the metallic ribs. So we'll create a material for ribs, create a property for ribs, and create a component for ribs, where we keep those elements in the different components as ribs. So first we will create the material as ribs. So we'll enter the material name as aluminium 2024 with a thickness that is T3. That is the code of the material as shown in the table. You can see here aluminium 2024 T3. So we'll select the type as isotropic, card image will be mat 1 and click on create edit. We'll enter the values of E, nu and rho as given in the table. So the values of E is given as 10.6 e to the power 6. The value of nu is 0.33 and the value of rho is 0.1. So we have entered these details. Then we will click return. Again we will click return to go back to the main menu. So on the model browser, if I minimize these things, on the material data you can see my new material, that is aluminium 2024 T3 has been created. Now I will create a property for the materials. So I will enter the property name, say ribs. Select the type as 2D because these are the 2D elements. Card image as P shell. Material will be aluminium. Click on create edit, enter the value of thickness as 1 mm. Click return, again click return to go back to the main menu, and we'll cross check it on the model browser that my my property is also created. Now the next step is to create component for this. So I will create a component as I will enter the name it as ribs. We'll select the property, say ribs, and click on create. So my component is also created. So property collector called rib has been created. It has a P shell definition with a thickness of 1. It also refers the aluminium 2024 material. So I have defined all these parameters. Now we will create material and geometric properties using HyperLaminate. So I will click return to go back to the main menu and enter to the new menu as HyperLaminate. So I will go to 2D page. On 2D page I will click on HyperLaminate to define the materials using HyperLaminate. So the first step before defining these materials is we will create a mat 8 card image of material. So I will click on mat 8, right click and click on new. So I will create a material as mat 8. Enter the name of the material as glass fiber, glass fabric. Enter the values of E, nu, rho and all these things as shown in the image as given in the table, the material database table. So I will enter the value of E as 4.0 e to the power 6. Then I will enter the value of E2 as 6.0 e to the power 6, NU21 as 0.1. These details you can find it on Google or in the theory of machines or strength of material books. The value of G12 as 8 lakhs. G1Z also as 8 lakhs. This will also be the same. Then the value of rho is 0.07 and the value of xt is 35,000. This is also 35,000 and this is also 35,000. So I have created a material as glass fabric and click on apply. So my material is defined. In the similar manner, I will create one more material as core. So I will click on mat 8, new, rename it as core, enter the value of E as given in the table, that is 2000, E2 will be 4000, NU1 is 0.3, G12 will be 3000, this will be 4000, this will be 4000, value of rho will be 0.001074, xt will be 500, xc will be 500, yt will be 500. So I have created this material also and click on apply. So I have created two materials as glass fabric and core. Then I will create a composite laminates using HyperLaminate. So to create it, we will click on pcomp, right click on it and click on new, rename it as inboard section, top. In the stacking sequence convection, I will select the convection as symmetric mid layer. We'll select the material as glass fabric. Thickness I will enter as 0.25. Orientation will be 0. I will add apply and click on thrice to add 3 plies and edit it here itself. So I will now edit the ply layup order. So my first ply will be glass fabric with a thickness of 0.25, orientation will be 90 degrees. My second will be core with a thickness of 0.5, orientation to 45 degrees. My third will be glass fabric again with the orientation of 0 degrees. And we'll click on update. Now we will create one more laminate as inboard section bottom. So I will right click here and you can directly duplicate this. We will rename it as inboard section bottom. Keeping all the parameters as it is, we'll update it. Similarly, we will update the orientation of other plies. So we'll start with the first outboard section bottom. We'll enter the value of 90, 45 and 0 and update it. Then the top one, 90, 45, 0, update. Midspan section bottom, 90, 45, 0, update, and midspan section top will be 90, 45 and say update. So in this way I have updated all the laminates, that is composite laminates. Then click on file and exit. So in this way we will exit the HyperLaminate panel. So as I already told you that we can do the same thing in by going to material collector. So I will show you how. If you want to create a glass fabric, you can go to material collector, select the type as orthotropic and card image as mat 8. Click on, you cannot click on create edit as is already created. So I will show you by creating update edit. You can input these values So this way you can also create. Similarly, properties, you can create a properties for inboard section bottom, like, and say update. You can see these things, you can update it. So the things you can update here as well as using HyperLaminate. HyperLaminate is more user friendly. That's why I suggested to use HyperLaminate whenever you are performing any composite optimization. So next step, after this, I will click return and again go back to the main menu. So my next step after applying or creating the materials and properties for composites is to assign newly created properties to associated components. So I will go to component, update, inboard section top with inboard section top, and update. Then inboard section bottom with inboard section bottom, update. Then midspan section top with midspan section top is updated. Midspan section bottom is updated with midspan section bottom. I will re-update it. Output section top with output section top, update. Output section bottom with output section bottom, and update. So I have updated all the properties. Now we will organize the elements into their respective component characters. Currently, if I off this, so you can see all the elements are in one single component. If I off this tail, all the elements will get hide. So I will organize these elements into respective components so that it will get required properties and materials. The different sections of the component, the model will get different properties and materials which I have created. So I click return to go back to the main menu. So before processing to organize this model, firstly I will go press O from my keyboard and go to mesh, enter the feature angle as 37 degree. So whenever I will select it by face panel, I will select the appropriate number of elements, that is the feature angle. So if the angle is more than that, it will not select the element on that surface. So in this way, this is done. So this will allow us to select elements by feature angle. So I will click return. Now we'll go to tools, organize panel to organize the elements into different components. So go to tools, organize, this is the panel. Click on the elements, click by face, select any one element on the first. Destination component is output section top, elements by face, click on move. Then midspan section top, select any one element by face, move. Inboard section top, select the element by face, move. Similarly, on the bottom side, output section bottom, select the element by face, move. Midspan section bottom, select the element by face and click on move. Click reject. Select midspan section bottom, select the elements by face, move. Then inboard section bottom, select the element biface, and move. So all these elements are organized into their respective component collectors so that the material properties will assign according to their components. Then right click on tail and click on isolate only, so you can see the ribs only. Then select the destination components as ribs, select all the elements of the ribs and say move. So right click on this and say delete. So this component doesn't have any elements, I will delete the empty component. So now you can see all the elements are assigned to their respective components. After that, my next step is to orient the element which refers composite properties. So we will orient them. So I will click return to go back to the main menu. So on tools page itself, I will click on normals. On the tools page, we will click on normals to orient all the elements normal into one single direction. Make sure the element radio button is selected. Select the entity selector type as element. Select the element by collector and check the box in front of ribs and select. Click on display normals to see the normals. You can increase the size also. So as you can see, the normals are in this direction. Then click on element entity selector and click on reverse. So apart from this ribs, all the elements will get highlighted. And click on display normals. So you can see, if I will lower down it, so the elements are having the vector orientation in different directions. You can see here. So what I will do, you can see by color also. So they all are in different directions. Then click on element under orientation and select any one element whose direction is pointing inwards, because I want all them inwards. So I will select this, as this one is pointing inward, and then we will click on adjust normals. Again we will see normals, elements, by collector, ribs, select, reverse, and display normals. Adjust normals, or we can say reverse the normals. We will lower the size inverse normals. Select this and adjust the normals. So all of them are pointing inwards now. If I lower the size to 1, you can see all of them are pointing inwards. So now we will click return. Then from 2D page, I will click on composites and orient the composite properties. So firstly we will select the radio button as material orientation. So I will select elements by collector ribs and say reverse. So all the elements of the skin I have selected. In the material orient vector method, I will select by vector and select z-axis. Select any one and say project. So all my material orientation is along one axis. Composite laminates material orientation is along one axis. So I will click return now. So this orients the local x of each of the selected elements to be the projection of global z-axis. This is displayed graphically by the small white arrows that appear on each of the elements. Having defined the local x and z-axis of the elements belong to the component collector inboard section, top and bottom, midspan section, top and bottom, outboard section, top and bottom. We have fully established the local orientation of each element referencing a composite laminate. Now we will create a static and buckling subcases. So three loading scenarios are to be considered in this exercise. One where the tail experiences pressure load on the bottom skin, a second where the tail experiences a tip load, and a third where the tail experiences both pressure and tip load simultaneously. Currently we have a load collector containing pressure load and another containing tip load, but we do not have a load collector containing both together. So we need to create a load collector in which a combination of load collectors, pressure and tip load. So I will create a load collector, combined load collector. So I will click on load collector icon, click on create radio button, enter the load collector name as combined, enter the card image as load, click on create edit, enter the load set numbers 2. The values of S here stands for the scale factor, S1 and S2 is for the respective load collectors. So I will select L1 as pressure and L2 as tip load. Enter the scale factor as 1, here also 1. If I want to magnify any one of the load collector, I can enter the scale factor value here. So during the combination of loading, the one will get magnified, or if you want both to be magnified or enhanced by a particular scale factor value, you can put it here. So S1 and S2 is for the respective load collectors magnification. Click return, again click return to go back to the main menu. So you can see my load collector combined has been created. Now we will create a static and associated buckling subcases. So to create the subcases, I will go to utility menu. In utility menu, we will select FEA. Under the load step, we will click on buckling. So create buckling subcase window will appear. We will enter the name as pressure only. Select the card as EIGRL, V1 value as 0, V2 value you can keep it blank. This indicates that the lower bound of eigenvalue extraction is 0. This prevents negative buckling modes being calculated. Negative buckling modes indicate the buckling will not occur in loading if loading is reversed. So V2 is the upper bound of the eigenvalue extraction. We will choose a number of modes to calculate instead of range of eigenvalues for this exercise. So enter the value of ND as 10. So this requires that 10 lowest buckling modes which are greater than V1, that is initial eigenvalue, will be calculated. Select the load as pressure and SPC as constraints and click on create. So we have now created a linear static subcase called pressure only, which combines the pressure load in load collector pressure with the single point constraint in the load collector constraint. And associated buckling eigenvalue subcase called pressure only is created, which will calculate the first 10 buckling modes, which is greater than 0.04 pressure only static subcase. Now we will create one more load collector as tip load only. So I will enter the name as tip load only. Keep these values as it is. Loading will be tip load. Constraints, SPC will be constraint and create. So my second subcase is created. Now we will create the third one as combo. All the values will be same, just the load will be combined, SPC will be constrained and say create. So my third load case is also created. So I will close this window and go to the model browser. On model browser you can see pressure only, buckling pressure, tip load only, buckling tip load, combo and buckling combination load step has been created. So once I will run this analysis, I will get the 6 different results of the different cases for the different cases. Now the next step is to request stress, strain and failure results for composite laminates. So stress, strain and failure results are not output by default of composite laminates. These must be requested. So I will go to control cards. From the card edit, switch to properties by selecting props. Select props as outboard section top. Select, click on edit. The PCOMP card image for the outboard section top laminate appears in the lower portion of the display area. So now in FT we will click on Hill. So this activates failure theory calculation. If you click HILL, a list of other failure theories pop up, but we will use the HILL failure criteria for this exercise. So these are the different theories of failure. Then click SB and enter the value as 3500. This is the interlaminate shear strength of the laminate, which is bonding material shear strength 3.5 KSI is an assumed value as no material data was provided. Then we will click on button beneath South 1 S out and click yes for all. This requests stress and strain results to be the output for ply 1. or to the all the 5 plies. Then click return. Similarly, we will update these SPS 3500 S out, yes. Then bottom, edit 3500 S out will be yes. Then midspan section top 3500 S out, yes, 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 and yes. Then inboard section bottom 3500 stress output will be yes for all the laminates. This will be 3500 as output, that is stress output, stress and strain output for all the 5 laminates. So I have updated all these. Then we'll click return to go back to the main menu. Then we'll go to analysis page. In analysis page, we will click on control cards. Then we will select global output request from the list of the cards available. And make sure the C strain is selected from the list of the cards. And C stress. So this will help us to get the required details. So I will click return. Again I will click return to go back to the main menu. Now we will perform a baseline finite element analysis. So I will save this file. And perform a baseline analysis. So to perform a baseline analysis, I will go to analysis, OptiStruct, select the export option to all, run option to analysis instead of OptiStruct. Memory option will keep as default and click on OptiStruct. So this will start the analysis process. So now as you can see, my analysis has been completed. So I will click on results to view the results using HyperView. Also, we will review the .out file of the analysis, summary file. Apart from this result. So I will open this. Here you will find .out file. You can open it in a notepad or textpad or wordpad. So this file contains a summary of finite element model, a summary of optimization parameters, memory and disk space analysis results. So if you scroll it down, you can find all these details. So we'll scroll it down to analysis results. So you can see here, these are the analysis results, different subcases. and modes and buckling eigenvalues. Now we will review the displacement results. So I will open HyperView, click on contour, displacement, apply. Then stresses values. Then we will see the stress values, elemental stresses. Click on measures to see the maximum or minimum. So this is the maximum stress. We will select the ribs one. So I will select it by or you can all these and click on display and say apply. So these are the stress values on the ribs. Then we can also select, click on show composite failure stresses. So this is the composite failure stresses. So after calculating the failure indices for individual plies, OptiStruct calculates the potential failure index for the composite shell elements. This is based on the premises that failure of a single layer qualifies as failure of the composite. Thus, the failure index of composite elements is calculated as maximum of all the computed ply and bounding failure indices. So you can also select bond failures for the different bonds. And you can change the loadings. So this is for combined results. So in this way, I have completed the base run analysis and get the desired results of base run analysis. Now we will perform the size optimization and compare the results with this initial design. So I will close the HyperView, open the HyperMesh again, close the solver window too. Click return to go back to the main menu. So to start with, my first step is to create and reference a thickness design variable for a metallic ribs. So I will go to analysis, optimization. In optimization, I will select gauges, gauge panel, which is in second column, second row. I'll select the radio button as create. Click on properties and select ribs from the list of the available properties. We'll make sure the top toggle is selected to value from the property. This sets the initial value of design variable to be the thickness value defined on the property card. Then toggle the lower bound percentage to lower bound and enter the value as 0.01. This sets the lower bound for the design variable, and upper bound value I will enter as 2. This sets the upper bound for design variable. We'll make sure the type is selected as P shell T, and also it is separate design variable for each property toggle is selected. Then we will click on create and click return twice. So in this way I have created a reference thickness variable for metallic ribs. Now next step is to create a design variable for composite laminates. We will use HyperLaminate again to do that. So I will go to a 2D page, HyperLaminate. So this time we will click on DSVAR, that is design variable. Right click on it and click on new. Enter the design variable name as ISTGF underscore TH, that is inboard section top glass fabric thickness. Enter the initial value as 0.25, lower bound as 0.01, upper bound as 1, and click apply. In a similar manner, we will create one more design variable as ISBGF, that is inboard section bottom glass fabric thickness. So I will duplicate this, rename as ISTBGF underscore thickness. Initial value will be 0.25, lower bound will be 0.01, upper bound will be 1, and say apply. So I have created these two. Now we will right click on the others and update them. So I will start with MST, that is midsection glass fiber. So we will review these values, like the initial value is 0.25, lower bound 0.01, upper bound is 1. Midsection bottom, the values will be 0.25, 0.01 and 1. Outboard section top 0.25, 0.01 and 1. Outboard section bottom 0.25, 0.01, 1. Inboard section top 0.5, 0.01 and 2. Inboard section 0.05, bottom 0.01 and 2. Mid section top 0.5, 0.01 and 2. Mid section bottom 0.5, 0.01 and 2. Outboard section core 0.05, 0.01, 2, and for outboard section bottom core, initial value is 0.5 and lower bound is 0.01 and upper bound will be 2. So total 12 composite design variables now exist. One for the thickness of glass fabric for each composite laminate component, and the other for the thickness of the core for each composite laminate components. Then we will update the composite laminate properties and design variable using HyperLaminate. So in PComp, select inboard section top. Check the box in front of optimization. For the first row, select in the play layup order, in the thickness design variable, select inboard section glass fiber, top glass fiber. So inboard section top glass fiber thickness. Then inboard section thickness core and inboard section glass fiber thickness. So I am defining the design variables with the respective laminates. Click update laminate. Similarly, select the bottom one, check the box in front of optimization. Bottom section glass fiber, inboard section bottom core, and inboard section bottom glass fiber, update laminate. Just cross check it with others. As you can see, it's already updated. Then click on file and exit to go back to the HyperMesh GUI and exit the HyperLaminate. Now we will create a mass, static stress and composite failure responses. So now we will start creating the responses for my optimization process. So we'll go to analysis page. In analysis page, we will click on optimization panel. In optimization panel, we will click on responses. Enter the response name as mass. Select the response type as mass. Keeping all the other parameters as it is, click on create. So the optimization response mass, which is the total mass of structure, is created. Enter the response name as VM stresses. Select the response type as static stresses from the drop box, static stresses. From the properties, select ribs collector. Select it to von Mises stresses for both the surfaces. Click create. So the optimization response von Mises stresses, which is the von Mises stresses for metallic rib, is created. Now create one more response as HL IST. Response type as composite failures. Select the property as inboard section top. Select. From the switch properties, select hill and select the all plies from the list of the options available. Click on create. So my next is created. Now create the other inboard section bottom, property as inboard section bottom, keeping all the parameters as it is. Then outboard section bottom, create. Outboard section top, create. Midspan section top, and midspan section bottom. click on the response and enter the value as buckle. Select the response type as buckling. Number of modes to be 1 and say click on create. So the optimization response buckle, which is the lowest calculated buckling mode for the structure, is created. So now we will click on return to go back to the main menu. On the model browser you can see my different responses is now been created. Now the next step is to create the constraint and objective. So finally the constraint and objective must be defined. We will attempt to minimize the total mass of the structure while keeping the von Mises stress in the metallic rib fibers below yield, the composite failure index of the composite skin below 1 and the buckling mode of the structure above 1. So click on deconstraint to define the constraint. Enter the constraint name as constraint 1. Select the response as von Mises stresses. Check the box in front of upper bound and enter the value as 50,000. Click on load step and select pressure only, tip load only, and combo, and click select. Then click on create. So if we scroll it down, you can see my constraint is defined. I will minimize these so it will be easy for you to see them in the screens. So my constraint on the von Mises stresses of metallic ribs to be less than 50 ASI for all static subcases. Then constraint second, response as HLIST. Check the box in front of upper bound and enter the value as 1. Select the same load steps, pressure, tip, and combine all the three. Click create. So this defines a constraints on Hill failure criteria of inboard section top laminate to be less than 1 for all the static subcases. So similarly we will create for the others. Inboard section bottom, select create. Outboard section bottom, select create. Outboard section top, select create. Midsection top, select create. Midsection bottom, pressure, tip, combo, and create. So in this way I have created 7 constraints for different Hill failure responses. Then constraint 8, response buckle. Uncheck the upper bound and select the lower bound and enter the lower bound value as 1. Select the load step as pressure, buckle tip load, buckle combo. Create. So this defines a constraint on the lowest calculated buckling mode for a structure to be greater than 1 for all the linear buckling subcases. Now click return. Now we will define objective for this optimization. So I will click on objective. So objective is to minimize the response mass and click create. So my objective is also defined. Now we will create additional run parameters to aid buckling constraints. I will click return to go back to the optimization panel. Then click on opti control. So for the buckling constraint to be effectively maintained, an additional parameters need to be defined. Check the box preceding maximum buckle, that is max buck. So automatically you can see the G buckling is checked. So together these two options ensure that up to 10 modes are considered in the buckling constraint. Then click return. Again click return. So I will save the file in a new folder. Go to analysis page, OptiStruct, run option to optimization, and click on OptiStruct to start the solver. So in this way the solver is started. So as you can see, it's still going on. Once it will get finished, you'll see the results. So you can see that optimization has converged and feasible design has achieved. So I will click on results to view the results of size optimization. So I will close this, split the windows into two, open the file of H3D, apply. Say we'll check one of the parameters, say displacement. So this is the optimized design. So I will first check the optimized design. So where the stacking sequence you can see elemental thickness and ply thickness values. Also you can see the reports for the different iterations. Now we will see the displacement results also. So let's see for the pressure one. Open H3D, apply. So pressure, this is the result for pressure before optimization and after optimization. So this is the displacement values for the load cases. Similarly, we will see the stress values.
for the same load case. So in this way you can compare the results of the optimization before and after the optimization. So I will close this. In this way I have ended with the first tutorial. So I will click new. Now we will move to the next, that is free sizing nonlinear gap optimization of airplane wing rib. In this tutorial, an existing finite element model of aluminum wing rib model will be used to demonstrate how to do free sizing optimization using OptiStruct. Hyperview will be used to post-process the thickness pattern in the rib. There are 4 shell components in the model: the mounting flange, the web, the top and the bottom flanges, and the lug. The web is connected to the lug by gap element. Appropriate properties, loads, boundary conditions, and nonlinear subcases have already been defined in the model. The design region is the web and the rest of the components are non-design. Web means the yellow region. Since a large portion of aerospace components are shell structure which are manufacturable by machining or milling operation, free sizing optimization is very suitable for those components. To understand the limitation of topology optimization for such application on nonlinear gap, topology optimization will also be done on the wing rib. The optimization problem for this tutorial is, my objective is to minimize the weighted compliances. My constraint is the volume fraction of the web should be less than 0.3. Design variable for free sizing optimization is thickness of each shell element in the design space. Design variable for topology optimization is element density of each element in the design domain. In this tutorial, we will see how to set up a free size optimization with nonlinear gap element, post-process the thickness convergence in the design domain, set up a topology optimization with nonlinear gap elements, post-process the material distribution in design domain, review and compare the results from free size optimization and topology optimization. So I will open the model in HyperMesh. So I will click open. So this is my model file with material, properties, components, load collector, load step, everything predefined. So I will directly start with the optimization processes. So I will start off this so that I can only see the model. So this is my model. This is my design space. Rest everything is non-design. So I will go to set up an optimization problem. I will go to analysis, optimization. So first we are going to perform a free sizing optimization process. So first step is to create a design variable for free size optimization. I will click on free size, enter the design variable name as shells, select the type as P shell, click on props and select the property as web, select and click on create. Now we will add some manufacturing constraint on free sizing. So click on parameters, click on design variable and select shells which we have created earlier. Toggle the minimum member off to minimum dimension and enter the value as 2. And click on update. Then we will create optimization responses, objective and constraints. So I will click return. Then we will click on responses to define the optimization responses. Enter the response name as wcomp. Select the response type as weighted compliances. Select the load step, couple, vertical and pressure, both. Click return. Then click on create. Now we will create the other response as volume fraction. Select the response type as volume fraction. Keep all the parameters as it is and click create. So my design variable response is defined. Now we will define the constraints. So I will click on D constraint. Enter the constraint name as volume. Response type as volume fraction. Upper bound is 0.3. Click create. Click return to go back to the optimization panel. Then we will define the objective. My objective is to minimize the weighted compliances. Click return, click create and click return twice to go back to the main menu. So in this way I have defined the free sizing nonlinear gap analysis optimization process. Now I will save the file and do the optimization process. So run one, that is free size, save, analysis, OptiStruct, and click on OptiStruct to start the solver window. So you can see this, it's going on iterating the optimization process. So now as you can see, a message has appeared that optimization has converged and feasible design has achieved with satisfying all the constraints. I will click on results. So now we will see the results. So I will off all the components and only keep the web one. Select the last iteration, go to contour, element thickness. So this is the element thickness distribution. So these are the elements where the thickness has to be 0.1. Other than that, you can minimize the thickness of the other areas. So as we can see from the figure, the result from the free sizing optimization is a web which optimizes thickness distribution that can be reduced subsequently into large zone for simplification of manufacturing process. Moreover, the design obtained from the free sizing offers the freedom to create cavities, ribs and vary thickness simultaneously, which is not possible by topography optimization. So now we will set up a topography optimization process. I will close this. I will also close this. Now we will delete the design variables for pre-sizing. And go to analysis optimization topology. So click on create. Enter the name as shells. P-type, select web. Select and create. Add some manufacturing constraints for topology optimization. So I'll go to parameters. Select shells. Minimum number of minimum dimension to 2. Click update. Click return to go back to the main menu. So keeping all the other parameters as it is, I have just changed the design variable from free sizing to topology optimization and see what difference it has. So I will enter it as run 2, save, go to analysis, OptiStruct, and start the solver. We'll see what are these results come like. Okay, so I will save this file in some other location. Save, analysis, OptiStruct, increase the default memory and try to solve it again. That was the error for the memory allocation. So my system is not getting proper memory where I have saved the file to solve it. So that's why I just changed the location to give him the proper memory. So it started solving, as you can see. So now as you can see, my optimization has converged and feasible design has achieved. So I will click on results to view the results in HyperView. So I will isolate this one only. Element densities, select the last iteration and say apply. So this is the material distribution which I get from the optimization process. So result from topology optimization shows a truss type design with extensive cavities and voids, while the result from pre-sizing optimization tends to come up with shear planes. While solid voids density distribution is only choice for solid elements. For shell structures, intermediate densities can be interpreted as different thicknesses, and panelizing them could result in potentially insufficient shell structures. Moreover, since a large portion of aerospace structures are shell structures, a shear plane type design is often desirable for manufacturing purposes, especially for machine milled shell structures. Pre-sizing optimization can improve to be very beneficial in those situations. So you can see that. So truss type structure instead of variable in thickness. So in this way, we have ended with this tutorial. So I will click new. We'll move to the next tutorial. Now we will see the next tutorial, that is manufacturing constraint in precise optimization of a composite structure. One of the advantages with composite material is that the structural performance can be controlled precisely by choosing the appropriate ply thicknesses, ply orientation, stacking sequence, ply material, and so on. The ability to vary many different parameters provides greater flexibility, but at the same time it is tougher to optimize the part as the number of design variables increases many folds. OptiStruct has the ability to directly or indirectly optimize the ply thickness, ply orientation, and stacking sequence of the composite structure. Pre-sizing optimization handles the thickness of each ply in each element as a design variable and optimizes the structure by determining the optimal thickness distribution of each ply in the laminate. Please refer the following pages in OptiStruct user guide to get more details. For several reasons, every composite manufacturer has their own manufacturability standards for the laminated composite. These additional manufacturing constraints are to be included for pre-sizing optimization to achieve an acceptable manufacturing solution. OptiStruct supports different manufacturability constraints that can be defined with pre-sizing optimization. This tutorial will help us to explain the procedure used to define the manufacturing constraint in pre-size optimization of composite structures. The optimization problem in this tutorial may be stated as: my objective will be to minimize the mass. My constraint is to the displacement of the selected 6 nodes should be less than 3 mm. The design variable is the thickness of each ply of each element in the design space. In this tutorial, we will set up a free size optimization with the following manufacturing constraints. Minimum laminate thickness of 0.2, ply thickness should be at least 10% and at most 60% of total laminate thickness. Defined for all the plies in the design space. The thickness of ply with an ply angle of 45 degrees to be the same as the thickness of ply with a ply angle of minus 45 degrees. In this tutorial, we will see set up a free size optimization with manufacturing constraint, post-process the free size optimization results. So we will open this model in HyperMesh. So this is my model of the wing ribs. So we'll start off with setting up a free sizing optimization with manufacturing constraints. So the basic properties are predefined in this model. So we'll directly start off with free sizing optimization. So I'll go to analysis page optimization. Click on free size. Select the create radio button. Enter the design variable name as skin. Select the type as PCOMG. Click on the property and select top skin, bottom skin. Select and click on create. So this will create the design variable for free sizing optimization. Then we will add a minimum dimension manufacturing constraint for free sizing optimization. So we will select parameters, select the skin, minimum dimension to 5. So this step defines the minimum member size control to be 5. Member size control gives you some control over the member size in the final free size design, and the resulting structure will have a discrete member that are easy to interpret during the post processing. Then click on update to update this manufacturing constraint. Then add minimum thickness manufacturing constraint for free sizing optimization. So I will click return. Go to composite. Click on design variable. In the laminate thickness, minimum thickness of to thickness, and enter the minimum thickness as 0.2. Click update and click on this edit button. Then select ply percentage. enter the value as 4. So P angle stands for ply orientation to which the ply percentage constraints are applied. PP minimum stands for minimum ply percentage thickness for the ply constraint. PP maximum stands for maximum ply percentage thickness for ply percentage. And PT man stands for manufacturable ply thickness. So enter the value 0 as the P angle. PP minimum value enter 0.1. PP maximum enter 0.6. Then 45.1, 0.6, then minus 45.1, 0.6, 90.1, 0.6. Check the box in front of balance. So balance flag indicating that a balancing constraint is applied. B angle, the balance angle 1, first ply orientation to which the balance constraint is applied. B angle 2, second ply orientation to which the balance ply orientation is applied. So enter the value 45 and minus 45. Click return. Go to analysis, optimization. So this is updated. So now you can see this is the updated flash stacking sequence. Now click return to go back to the optimization panel. The next step is to will create displacement and mass responses. So I will click on responses, enter the response name as displacement, response type as static displacement. Select the nodes by set, select those nodes. So these are the nodes on which I want the displacement. Choose degrees of freedom 3, click create. Enter the response name as mass, response type as mass. Keeping all the parameters as it is, click on create. Now we will create the constraint. So I will enter the D constraint. Enter the D constraint name as displacement constraint. Response type as displacement. Check the upper bound to be 2, load step. as subcase 1 and 2 both. Click create. Now define the objective. My objective is to minimize the mass. Create. Return twice. Now I will save this file. So now I will run this file. So I will go to analysis, OptiStruct, export option to all, run option to optimization, and click on OptiStruct to solve this model. So you can see my solver has started. So as you can see, my analysis has been converged and design has been achieved, the feasible design has been achieved. So I will open the hyperview to view the results. So we'll click on apply, simple. So these are the manufacturing constraints for the different orientations. So in this way, you can solve the composite laminates with the manufacturing constraints. So in this way, I have ended with the online training session day 8 size optimization part 2, which is the last part of this day 8. Thank you very much for watching this video or attending the session. To improve the online training session, please help us by sharing your valuable comments at edu-support@indiarollday.com. Also, like this training series, then also your comments will be valuable for us, so that it will motivate us to work in this direction further. Thank you very much.